Okay, so we'll redo chapter 5 review because the voice was not clear yesterday. So, biology. I'll go through the most important slides that will come in the final, and they are very important. Well, okay, so let's go and check. These are the feeding strategies for microorganisms. It's like us. The only way to eat is through our mouth. Well, for these microorganisms, there is several various strategies for feeding. It's either absorption, photosynthesis, or ingestion, like us. Okay, the absorption, uptake of dissolved nutrient, fungi, fixation of light energy into simple organic molecules, the photosynthesis, for example, plants, and ingestion, like intake of particulate nutrient, like animals and humans. Well, also, it is very important to study the microorganisms and use them for our benefit. So we are using microorganisms to treat wastewater. And this is a wonderful approach. And also to clean groundwater through groundwater bioremediation. Okay, so let's look at the next slide. That's important. How could we measure the concentration of biomass, microorganism content, bacterial content? Is by using the population size technique, either through dry weight, if you see it gram dry weight, or organic carbon content, gram carbon, or chlorophyll content, gram chlorophyll. The rule in the fate of fecal bacteria, the chart of the surface water, is also, the dynamics are also important to study. Okay, so it's either we do the modeling of the population growth through the mass balance, and the first of all, we should go ahead with these equations. The first equation is exponential growth. And I said in the class that this is not realistic. Logistic is more realistic. Monod is the best model that we might apply to microorganisms and check their growth easily. The exponential growth is following this equation. This is the growth according to this technique. If you integrate that, it will be like this. This is the biomass at time t. This is the biomass at time 0. Mu max, the maximum growth rate. Kd is the constant death rate. And t is the time. And if you want to do it like this could be exchanged with this one, because mu net is equal to mu max minus Kd. Well, if someone asks you what's mu net, you could find it by mu max minus Kd. This is a good example to look at. Okay. The second one is the logistic growth. The logistic growth is after you take the effect of carrying capacity, and here it's also called unlimited growth. Okay, like the one we had before. I mean, this is limited growth. The exponential growth, that there's some suitable carrying capacity here. The previous one, the exponential growth is the unlimited growth. The logistic growth is there is a carrying capacity here, so there is some limitation, maximum limitation. So in the logistic growth, we add up. Remember this one, the whole thing was times x. We added the K, the carrying capacity K, milligram dry weight per liter. So this is the equation for the logistic, and you can see that this is an example we just did in the class. I just want you to go to the most important thing. Although in the final, none of these two will come in the exam. The model is very important and it will come in the final. It's explain the population organisms in nature compared to logistic growth model. It's very close, but the Monod model is more important. Here that the growth is limited by what? Renewable resources. And the relationship between nutrient and population is described by the Monod model. This is the Monod model. Ks, it is the half saturation constant milligram substrate per liter. Now, of course, S is substrate and mu max is the maximum growth rate and mu is specific growth rate and the unit is per day. If I give you a graph like this, substrate versus specific growth rate mu per day, and the curve will be like this. Most of the curves will be like this if you plot substrate versus specific growth rate. And I ask you, find me Ks. Remember Ks? This Ks. Find me Ks. Ks is a very important parameter. So how could we do it? Is first of all by extending a horizontal line with the curve, with the ultimate curve at the top, and then we call this mu max. Half of that, half of mu max, let's say here's 1, so half of it is 0.5. You go to the curve, you go down, and that is Ks. Ks in this side is 2.5 milligram per liter. Well, now, why we have to study Ks? Ks is a very important parameter. The lower the value of Ks, we can see that Ks will approach mu max at a lower substrate concentration. The lower value of Ks mean there is higher affinity of enzymes for substrate, which mean that the microorganisms has a great taste for the food, for the organic. Okay, so there is greater affinity of the enzymes for the substrate. The substrate is the food that the microorganism will be looking at. So we need it always lower Ks. We don't want Ks high. If Ks high, the microorganisms are not interested in the substrate, and that's not good. We need to make the Ks as low as possible. So the Monod equation, and then resource limited growth. Okay, you should look at this. We study that. If we make these in two separate cultures, this by itself will grow fine, and this will grow fine. But the problem is here that the Ks of this one is is lower than Ks of this one. Let's say Ks1 and Ks2. So Ks2 is lower than Ks1. So if you put them separately living, they will be fine. But if you put them together, oh, this one will eat more. Okay, and this one will die eventually, even though this is a bigger one. But we don't care about the size. We care about Ks. Okay, so you can see that grown separately, how they look like together. They're very close. And growing in a mixed culture together. Okay, and this one will grow and then die later on. Okay, so yield coefficient. We know that the yield coefficient is known by change of microorganisms over substrate change, and this is also was put into the equation that we had before. Okay, in the Monod equation, and ds over dt, change of substrate and change of microorganisms. This is how to account for the yield, and the yield was accounted when we put ds over dt. The example that's very important is this. Look at this example. And we did explain it in YouTube, and we just explained it in the class. So these are the standard mu max, Ks, yield, and Kd, and for the design biokinetic constant. And this is another example for simplified calculation of substrate and biomass. You don't have to go for this. What I need you to do is the following. Okay, so organisms. That one came in the quiz and will come in the final. Aerobic respiration. Some microorganisms, they use oxygen. And we call these microorganisms aerobic microorganisms. Okay? And some microorganisms will use anaerobic respiration. They don't need oxygen, anything but oxygen. This is anaerobic bacteria or anaerobic microorganisms, and this is aerobic microorganism because they use oxygen. The other one does not use oxygen. If there's oxygen, they will die. Okay? So the anaerobic microorganisms could do either breathe nitrate, not oxygen, manganese, ferric iron, sulfate, and sometimes organic compound as fermentation. So we don't have to worry about trophic structures, exam of exponential growth. Okay. Let's look at the oxygen demand. That's very important, BOD. Two things that we have to understand here. What is the definition of biochemical oxygen demand? That's very important. What is the unit for BOD? Milligram BOD. Milligram per liter of oxygen. Okay. Okay, so what is the meaning of BOD? You can see that BOD, this is a good definition of BOD, and that's very nice. BOD, it is the amount of oxygen utilized by microorganisms in performing the oxidation. Oxidation of what? Of organic. It is a measure of the strength of a water or wastewater. What is the meaning of that? The meaning that the greater the BOD, the greater the concentration of the organic matter. Okay. Could someone also see why this is happening? The fish kill. That happens also in Kuwait. All these fishes are dying at the top. Why? The only explanation is this. Please look at this explanation. It's very easy. We just explained it, and I think it's very important. Now we come to BOD equation itself. Okay. BOD, it's a total oxygen consumption. So if you plot time versus BOD in milligram per liter, you can see that the BOD will increase all the way until it reaches a maximum horizontal line. If you want to see, this is BOD. This is microorganisms breathing oxygen. Now, the other side, the food inside the sample, you can see it will go from high to low. While the cumulative oxygen will go from low to max. Okay, so these are two things, two curves that's being approached during the BOD analysis. This, when the food goes down to a minimum, time versus CBOD remaining, we use this equation. This is the food at any time t, substrate at any time t, and this is the initial substrate, and this is KL, constant KL, this is the time. This is the equation for the BOD. I don't know why the book make it YT. So BOD, I don't want to call it BOD5, I'll just call it BODT is equal L naught ultimate BOD 1 minus E minus KT. Okay, if that is BOD5, so this is going to be BOD5 and T would be 5. This is also just summarizing the two curves. This is the BOD5. Again, this is BOD at time T. And this is the food, the substrate that will come down with the eating, the degradation from the microorganisms. This is L naught. Okay, so now Thomas method, don't worry about it. This is good example. Look at it. It came to the final last year. So it's good to look at this example. Chemical oxygen demand. Now, the difference between BOD and COD, BOD uses the oxygen to degrade the organics. So the bacteria are breathing the oxygen to degrade the organics. This is the oxygen consumption as BOD. Now, COD, there is a strong oxidizing agent that will degrade the organics inside the sample. And this process called chemical oxygen demand. This is a very important slide. It came in every final exam. That BOD and COD, it could give you the indication. If you divide BOD over COD, it could give an indication if the waste is biodegradable or non-biodegradable. If it was close to 1, if it was close to 0.8, BOD 0.7, 0.6, 0.8 is very nice. 0.8, I'm totally sure if you put sugar, it's going to be 0.8 and 0.9 because microorganisms love sugar. It's a very good glucose source. So if it goes to 1, BOD over COD, close to 1, this is a good biodegradable waste or highly biodegradable waste. And every time the BOD over COD goes to 0, like if you go BOD over COD close to 0.1, now the waste will become non-biodegradable or poorly biodegradable. If BOD over COD is 0.01, this is poor. It cannot be, the microorganisms cannot biodegrade this waste. You have to do something. You have to do either dilution, add more fresh water, or you have to put genetically modified microorganisms, or you have to find a solution. So these are the two things we looked at. And this is final definitions, and I think this is good for chapter 5. Thank you.